All right, so numbers 3 and 4 just deal with finding the probability of events, but with just a different situation. It says use the spinner. For example, 3. Find the probability that you get an even number on your first spin and a number less than 3 on your second spin. So the notation for this, probability of even, comma, less than 3. That's showing that we're getting the probability of 2 events occurring. If I wanted a third event, I would say comma and put another event in there. So to get this, first of all, think about, are these events independent or dependent? So Elliot, do you think that getting even on your first spin and then a number less than 3 on your second spin are independent or dependent events? Independent. Why? Good. The second spin doesn't rely on the first spin. You could spin it all day long. They're never going to affect the next one, technically. Okay? And so what we get to do is just find the probability of an even and multiply it by the probability of getting less than 3. So what is the probability that we get an even? Look at your spinner. Jenna, when you're ready, let me know. What's the probability of getting the even? 4 out of 8. Okay, 4 out of 8. Then Tori, what's the probability that we get a number less than 3? 3 out of 8. Don't count the 3 because we want less than 3. So just the 2 out of 8. And then we just multiply those together. 4 times 8, or 4 times 2 is 8. 8 times 8 is 64. And then reduce your fraction or get decimals, either or. I'm going to write both. 8/64 is the same as 1/8. But you could write that as 0.125. Or, why don't we even, might as well, about 12.5%. I do not care which way you write your probabilities. So if you love percents, do percents. If you love fractions, fractions, decimals, doesn't matter. Okay, number 4 says 9 women and 6 men are on a committee. How many people are on our committee total? 15. It's usually helpful to do as you're reading your problem. 2 people are randomly chosen from the committee members to serve as chairperson and treasurer. Find the probability that both events A and B will occur if we let A be the chairperson is a man and B the treasurer is a woman. So we want the probability of getting A and B, which is, now we have to decide, are these independent or dependent events? What'd you say, Lane? Dependent, because if I pick a man out, right, are there less people now to choose from? Yeah, so that's affecting the chance for the next person to be chosen. So we're going to do the probability of A multiplied by the probability of B given that A has already occurred. And it's not really more math than you just have to think about it. So if I want to get the probability of A, that means I'm looking for, what's the chance that I chose a man out of this group? And so Hank, can you help me answer that question? Well, there's how many men, though? Oh, I see what you're doing. You want to still think about it as there's still 15 people we're choosing out of, right? There's 9 women and 6 men. How many of them are favorable? We want men, so 6 out of 15. I totally understand why you came up with those other numbers, though. So make sure that your bottom number is the total of the number you're drawing out of. So your total group has 15. 6 are the favorable outcomes. So we have a 6 and 15th chance of choosing a man. Now, if we assume the man has been chosen, that's what this means. Now, what's the chance that we choose a woman next? Tori? 9 out of 14. There's still 9 women because we're assuming we chose a man the first time. So now we have 9 women, but there's only 14 possible people left. And then we can calculate that probability, 6 times 9 and 15 times 14. So we get 54 over 210, which is 9/35. Or 0.25, did I do that right? 0.257. Or if you like fractions, about 25.7%. Any of these answers is fine. Does that make sense? So every time you're given a problem about probability, think, is it independent or dependent, and then you're okay. All right, the next one, we're going to actually compare independent and dependent events. Can't get this whole thing to show up on here. Okay, this says a bog, but that's supposed to say a bag. Contains 10 red marbles and 5 blue marbles. You randomly select 3 marbles from the bag. What's the probability that all 3 marbles are blue when A, you replace the marble after each time, or B, you do not replace, and then we're going to compare. So for A and B, we have 2 different events. Which one of these is the independent event? Tori? A, because we're taking a marble out, we're replacing it back in, so it starts all over again. Think about it that way. And so A is going to be independent. And so what we can do is say the probability of getting, and we want 3 blue marbles, so a blue followed by a blue followed by a blue. Blue, comma, blue, or your book sometimes puts ands in between each one. It's up to you, blue and blue and blue. Means I'm going to have to get the probability of getting a blue, multiply it by the probability of getting a blue, multiplied by the probability of getting a blue. We have 3 different things happening. We're going to draw a blue, draw a blue, draw a blue, hopefully. But every time we're replacing the blue one. So what's the chance that I get a blue out of this bag? Ooh, good. Some people would say 5 out of 10, but be careful. Tori said it's out of 15. We've got 10 red, 5 blue. We have 15 total. And so the chance that I get just the first blue is 5 out of 15. What's the chance that I get the second blue? Also 5 out of 15. Are you with me, Brittany? Okay. And then the chance I get the third blue? Also 5 out of 15. If you started doing this, though, and you kept drawing blues, you'd probably get suspicious because it's not that likely that this would happen, as you'll see once we multiply these together. What I prefer to do here, 5/15 is the same as what number? 1/3, right? 1/3. And so we could just do 1/3 times 1/3 times 1/3. That way we don't even need to have a calculator. We get 1/27. If you like a calculator, feel free to use it. I'm going to get the decimal number for those of you who like that, 0.037, or about 3.7%. So it's not very likely to draw a blue, then a blue, then a blue. Okay. In fact, it gets less likely every time because you keep multiplying by 1/3. Third less likely, kind of. Not less likely, but sort of. Yes?
I think I got number B.
Okay, wait a second, because I want to make sure we're doing the notation right. So part B says you're drawing a marble out and you're not replacing it. And so this is going to be dependent events. So we want the probability of blue and blue. That looks like band. Band. Oh, I don't need another and. So blue and blue and blue will be the probability of getting the blue the first time, but then followed by the probability of getting a blue given that we already got a blue, multiplied by the probability of getting a blue given that we already had 2 blues is kind of, I don't really know the exact best way for that notation. But and so, Cody, you think you know what you did? Don't give me the answer. Can you tell me what you did for the first?
I did 5/15.
Okay.
Times 4/14 and times 3/13.
Okay, so before you give me that answer, does that make sense to everybody? So we had 5 blue marbles out of 15, but then we kept that one out. And so, yeah, there's only 4 blue marbles in there, and there's only 14 total marbles. And then the next time, we're still keeping that out, so there's only 3 marbles left out of 13. Does that make sense? And so what did you get, Cody, when you multiplied all that together?
291st. It was a bigger number by you.
Oh, okay, 291sts. And then you got a bigger number and you simplified it. And then did you get the decimal also? Or not? Okay, that's fine. 0.022 or 2.2%. This notation you do not have to write out. I would just be concerned that as things get more complicated, you might care to. So for right now, if you just want to write it out, as long as you know what's going on, you're okay. I have a question, because I just thought of it as we were looking at this one. At what point, or would it not, would there ever be a probability of this happening to be, I'm wording it wrong, that the probability would be 0 if I just kept going? Like, what about getting the 4th one blue, and then the 5th one blue, and then the 6th one blue?
It would stop after 1/11.
Okay, yeah, if you kept going with this, you have 2/12ths, right?
Yeah.
And then 1/11th, and then 0/10ths, and then when you have a 0 on the top, and you multiply all the numbers together, you get a probability of 0. It's not possible to get a 6th blue one, right? Because there aren't 6 blue ones in there. And so with the dependent events, it's kind of interesting if you were to look at that pattern that you could possibly get 0 if you tried to do too many blues, more than what you have. Okay, before we jump into this next section on example 6 and 7, it doesn't really matter for number 6, but I want to look at that formula. You don't have to write this part yet, but I'm just going to show you something. Probability of A and B occurring for dependent events, we said was the probability of A multiplied by the probability of B given that A has occurred. Now, what if I only want to find a conditional probability, which is what's going to happen in example 7? Well, what I can do is rewrite this formula to solve for the probability of B given A. How would I get this yellow part that I highlighted alone? It's being multiplied by something, right? I could just divide that to the other side. So actually the formula for conditional probability, this you need to write down. I was just showing you where it comes from. Conditional probability formula says the probability of B given A is equal to the probability of A and B occurring divided by the probability of A. And that's just from this previous formula, just resolved for a different aspect or variable. And that's going to be important when we get down to example 7. If you get into later probabilities, the conditional probabilities can get pretty complicated, but for our examples, they won't be too bad. You'll see that they're going to give you the information you need, and you just have to know where to plug stuff in. Okay, example 6. Does anyone still need that up there? Hey, Cole, is my computer still on, like, showing what I'm doing? Okay. Okay, example 6 says, a quality control inspector checks for defective parts. The table shows the results of the inspector's work. So the way that this table works is you can see that in this row, these are all the ones that were defective, 5 and 24. So there's actually 29 defective parts. The non-defective parts, there were 208 plus 9, so 217 non-defective parts. When he did his test, this first column, the pass, these are the ones that passed his inspection. So 5 of the defective parts passed his inspection. That's probably not good, right? But 208 of the non-defective parts passed his inspection. That's good. Of the failing his inspection, 24 of the defective parts failed his inspection. That's probably good that they failed. We kind of wish all of the defective ones had failed, sort of the goal, but that doesn't usually happen. And then 9 of the non-defective parts failed his inspection. Okay, so that's just how this chart works. It's called a two-way table. What we want to do for part A is find what is the probability that a defective part actually passes. And so this is really, if you want the notation, the probability that a part passes given that it's actually defective. So think about the way that was worded. We want a defective part. We want to know what's the chance that a defective part actually passed. And so look at our chart here. We want to look at given defective. So out of all of the defective ones, which ones have actually passed? And so when you're doing this, you kind of look at your given part first, and that becomes your number on the bottom. And so all the defective parts total together to be 29. of those, which ones passed? So now we're looking just within those 29, and 5 of the ones in that 29 passed. So 5 out of 29, or 17.2%. That doesn't seem very good that he passed about 17% of the defective parts passed through and got sold on to the customer even though they were defective. Okay. Does that make sense? How would I write this next one? So it says, find the probability that a non-defective part passes. Tori? Do you know what this line means? Given. Yep, just given that non-defective. I'm just going to put non-D. Okay. So what numbers are going to go where? What do I really care to look for? What do you think, Cody?
8 out of 17.
Okay, so you looked at the total of the non-defective was 217. And then of those, 208 actually passed. So 208 out of 217 is about 96%, 0.959. So 95.9%. And that's probably a good thing. That way those get sold on to the customer. They don't get held back. Okay. Does that concept make sense? Conditional probability. So you're looking within one section in order to calculate it, basically. Okay, the last one that's about conditional probabilities, example 7 says, at a clothing store, 75% of the customers are buying pants. Only 20% of the customers buy pants and a belt. What is the probability that a customer who buys pants also buys a belt? And so we want to know the probability that a customer who buys pants also buys a belt. So we're saying if they've bought pants and then buy a belt. So it looks like this, belt, given that they've bought pants. I think that's going to be the trickiest part about setting it up, is knowing what are they really asking. We want to know that if they bought pants, what's the probability that they also bought a belt? So we only care, really, about the people who bought the pants. And so we need, on this one, to use this formula at the top of the page. This is why I put it in here. The probability of B given A, we take the probability of A and put it on the bottom. So this probability of just in this case, the probability of pants goes on the bottom. And on the top, the probability of A and B. And so that would be the probability of belt and pant. Belt and pants goes on the top. And then this is what I said. They're going to give you the numbers you need. You just have to know where they go. So what was the probability that someone bought belt with pants? So 20% of the customers buy belts and pants. 20% is your then chance that a randomly chosen person would buy belt and pants. And so this combined probability on the top, that'll be the 20%. And you can just leave it as 20. It's not going to hurt anything. And on the bottom, 75% bought pants. So 20 over 75 is 0.26 repeated, or about 27%. Cody.
Wait, wouldn't it just be 20 because it doesn't only 20% buy?
So this is saying 20% of all customers buy a pants and a belt. We want to know what is the chance that if they actually already bought pants, that they also bought a belt. So the 20% is talking about like every single customer who comes into the store. So there's some people who don't buy anything, right? But what we want is the people, out of the people who we know bought pants, which ones also bought the belt. And that, not which ones, but what's the probability that they also bought a belt. Does that make sense? And that's where this conditional probability of the probability of pants goes on the bottom, because we're restricting it to just those first. So we're looking at just these 75% of people first. We don't care about the 25% who didn't buy pants. Does that make sense logically?